So the textbook, some of you have already asked me questions about the textbook. So the textbooks that I listed on the syllabus here, that's the US edition. And some of you told me that there is an international edition using the SI units. Actually, when I was in grad school, I used this textbook back in China too. That's a Chinese version, not in Chinese, but in English, but it's published by a Chinese publisher. So and the copyright was given to the Chinese publisher. So yeah, I bought the Chinese version too. So I think both the US edition and the international edition work in our course. Because most of our analysis or theoretic discussions are pretty unit, not so unit sensitive. So either you use the SI units or the inch pound or inch Fs units. I think you will not have any difficulty in versus the information there. So so that's about the textbook. Any questions regarding the textbook? Especially for those students online. Those students online, do you guys have any questions regarding the textbook? You may send me some questions. So grading. So I think based on my experience, most of the students are very concerned about the grading system for any course. So here, this is the grading system that I'm going to use. The class attendance, 5% your final. Since it's a hybrid version, I think class attendance is very important for you to be successful in this course. So please make sure you can make most of the classes either online or on campus. Homework. Homework is as you can see here, 20%. It's a very also is a very important part to your final grade over here. Because you wanted to be good at structured dynamics, you do need a lot of practice, especially in interpreting different types of problems and doing a little bit math there to be able to find a solution. So I do expect all of you able to solve some typical problems independently. And all the homework problems will be from the textbook. So the textbook is there. And I think the one reason I selected today's textbook is because there are so many homework problems on the textbook. They're very good textbook. So that's about homework. And we will have 2 exams only. So that means both of them will be midterms. Both of them will be given to you before the final week. So no hurdle to take the final for this course. I think some of you may like it or some of you may not like it. That's this course. So to replace the final, I'm going to give you 2 projects besides the 2 exams here. So one project will be midterm project. Another one will be expected to be submitted in the final week. So one midterm project and a final project there. So two projects here. So you can see here regarding assignments, looks like assignments are almost equally weighted over there. So, so that's the percentage of the assignments for this course. Any questions from students online, especially? Here is the student. Okay, so then the system for me to give you letter grade is also attached here. The numerical numbers that I calculate based on your submission of all the assignments here give you letter grade on this table. Any questions regarding the grading here? Is this clear enough to you? Okay. No, any other questions? Yes. So about the exams, as you can see here, all exams are open book, open. And so there will be no makeup exams. So these exams. But in some cases, if you give me an advanced loading, at least 1 week, I think that you may have the job to do the scheduled exam dates for some other emergency characters there. So just maybe know at least 1 week, so that I can either reschedule the exam or give you some accommodation. You know, in advance, other than missing the exam and telling me that you take. So please schedule everything beforehand, other than give me some excuses. So that's the. So and since we have students online, so all exams will be online. All exams will be. So you can. So for students taking in person, you will take the exam online, the same like the online all students here. So some of you took my finance element analysis, so I'm online, so all the exams are online. So basically, I'll upload the exam questions to the Blackboard and make a time window for you, so that you need to finish all the exams within the time window, and scan your work and submit it back to the Blackboard. Yeah, I believe because we have done that for so many semesters. almost 2 years. So everybody's already familiar with that. So that's not a big issue to have exams online. So,
Professor, what will be the date of the exams again? I mean, I didn't hear you very well.
but I understand that in this case that you may refer to the other resources than the textbook itself or the lecture notes, but I would all of you take the exams independently without any consultation with friends or classmates. Yeah.
Right, but what are the dates again?
I think that taking exams is one of the best ways to learn new stuff, to tell yourself how much you have already learned. Okay, so that's the exams and homeworks. Yes.
Do we have dates for the midterm? You said the finals the week before finals.
Okay, so we will not have final over here.
Right.
So, sorry about this. Yeah, so
Do you have the date for the midterm?
the date for which one?
Midterm,
The midterm.
So the date is tentatively, or you can see here, the,
October 5th and November 9th.
yeah, like, are they Tuesdays? Oh,
That's next semester.
Oh, okay, sorry about that. Because previously this course was offered in fall semester and spring semester.
Right.
Okay, thank you for your reminder. I will fix that. So I would say tentatively should be so equivalently. If we say October 5th, that means we will have the first one around early March, the second one to be early April. Does that make sense? Homeworks. Since a lot of you found a lot of homeworks and stuff, we can do homeworks online many times. So yeah, so we need to further discuss that issue. About the topics to be covered. Yeah. So that's here I listed 9 topics to be covered. I think so this course was offered last time this course was offered was back in fall of 2019, about 2.5 years ago. And so last time we did cover all of these topics. So as you can see here, firstly, I'm going to introduce you on the general approach to formulate a structured dynamics problem. So how we interpret the real world and convert the real world problem to a structured dynamics problem or a mathematical problem. So in order to do that, we need to do some assumptions and simplifications, and so that's why it is very important to know the general approach to do a structured dynamics problem. So that's the first part. So the second part is a single degree of freedom, the free vibration. So that's in some cases, some real world problem can be simplified as a single degree. radar system there, so that we should be able to analyze it. The single degree of freedom. So we will talk about the pre-vibration, post-vibration, and after we covered the topics 1 through 4, we should be able to talk about the response and the design spectrum there regarding first phase. So part 5. So some of you may been working in the industry for a few years. So I believe most of you have already heard about response spectrum or the design spectrum. If you tie seismic laws to the structure, you do need to understand what do those two spectrums mean. Spectrum here. So that's part 5. And so under part 5, so the part 6 and part 7, we're going to talk about the multi-degree of freedom. So that's the I would say multi-degree of freedom system more close to the real world, such as if you have multiple story building, that kind of building is a multi-degree of freedom rather than a single degree of freedom system here. So it is very important to touch a little bit discussion about that. Because if in future some of you may be involved in designing of high-rise buildings, so that's why we need to understand a little bit background about the analysis of high-rise building. That's part 6 and 7. And part 8 and 9, that's a little bit theoretical background about some sampling numerical methods. So and in the part 8 and the part 9, you expect to be able to do a project to write some program. Sales purchase or in MATLAB. So how many of you have used MATLAB to do some scientific computing, like to doing matrix analysis? How many of you have used Excel to do a little bit program, not so advanced program, but a little program such as we put some functions here. Okay, I think all of you have developed some skill there. I think that should be adequate here. Typically, I will show you how to do that in both platforms, so that you can do a little bit numerical analysis using the approaches given in class, so that you can have a better answer, better understanding on the manage of the system. Okay, so that's the syllabus. That's the syllabus. It's some typos in the syllabus. Sorry about that. And fix that and update the revised one shortly, very shortly. So that's the first part of the night class. Any questions so far? So about the textbook, I highly recommend you to get the textbook. So that's a very classical textbook written by Professor Chopra from UC Berkeley. So UC Berkeley is a leading school in earthquake engineering and seismic research. So a lot of tools, database, and being developed by that school. Some of you have already used the SAP 2000. How many of you have used SAP 2000? Okay, very good. So actually, the SAP 2000 was developed by some professors from UC Berkeley back in 1980s. And then they commercialized that software, and then now becomes one of the standardized specialized tool for different types of design and analysis there. The amount of or
Professor, I have a quick question. Will you record these lectures?
professors from UC Berkeley. So I would say that textbook summarized
Professor, you hear me?
theoretic background as well as the most advanced technology for speed engineering and system testing and structural analysis there. Structural dynamics there. So it's a very good textbook. So that's the syllabus, and now the next step, I'm just going to give you an introduction on the structural dynamics. But firstly, stop the sharing. Say a I'm not share my screen firstly. Okay, the students are online. See my sharing of my YouTube.
Yes, I can see.
Okay, thank you. I'm just gonna play this YouTube video in classroom. And some of you may be able to watch the video from your WebEx platform. In case it does not work well, you should be able to access this video from your Blackboard system there. So there is a link to this video to
By chance, would you mind if you record the lecture?
internet too. But here I'm just gonna okay, so when you watch this videos, so the first video I would like to ask you to answer those questions. For video one. So actually, I prepared these questions on my OneNote on the cloud system there, but unfortunately, I cannot state it here. But I'm just gonna tap it. Guys here. So the first question here is, what are the major factors of vibration? Second question is, what type building is more all right. You know that? Yes. Feels too small. So when you watch the two videos, please keep the to here. So students online, can you guys see, or can you, ladies and gentlemen, online, can you see the questions here? So when you, okay, thank you, dear. So when you watch the video, please keep these two questions in mind to see whether you can answer them after you watch the video. So now let me go ahead to play the video here.
Earthquakes have always been a terrifying phenomenon, and they've become more deadly as our cities have grown, with collapsing buildings posing one of the largest risks. Why do buildings collapse in an earthquake, and how can it be prevented? If you've watched a lot of disaster films, you might have the idea that building collapse is caused directly by the ground beneath them shaking violently, or even splitting apart. But that's not really how it works. For one thing, most buildings are not located right on a fault line, and the shifting tectonic plates go much deeper than building foundations. So what's actually going on? In fact, the reality of earthquakes and their effect on buildings is a bit more complicated. To make sense of it, architects and engineers use models, like a two-dimensional array of lines representing columns and beams, or a single-line lollipop with circles representing the building's mass. Even when simplified to this degree, these models can be quite useful, as predicting a building's response to an earthquake is primarily a matter of physics. Most collapses that occur during earthquakes aren't actually caused by the earthquake itself. Instead, when the ground moves beneath a building, it displaces the foundation and lower levels, sending shock waves through the rest of the structure and causing it to vibrate back and forth. The strength of this oscillation depends on two main factors: the building's mass, which is concentrated at the bottom, and its stiffness, which is the force required to cause a certain amount of displacement. Along with the building's material type and the shape of its columns, stiffness is largely a matter of height. Shorter buildings tend to be stiffer and shift less, while taller buildings are more flexible. You might think that the solution is to build shorter buildings so that they shift as little as possible. But the 1985 Mexico City earthquake is a good example of why that's not the case. During the quake, many buildings between 6 and 15 stories tall collapsed. What's strange is that while shorter buildings nearby did keep standing, buildings taller than 15 stories were also less damaged. And the mid-sized buildings that collapsed were observed shaking far more violently than the earthquake itself. How is that possible? The answer has to do with something known as natural frequency. In an oscillating system, the frequency is how many back and forth movement cycles occur within a second. This is the inverse of the period, which is how many seconds it takes to complete one cycle. And a building's natural frequency, determined by its mass and stiffness, is the frequency that its vibrations will tend to cluster around. Increasing a building's mass slows down the rate at which it naturally vibrates, while increasing stiffness makes it vibrate faster. So in the equation representing their relationship, stiffness and natural frequency are proportional to one another, while mass and natural frequency are inversely proportional. What happened in Mexico City was an effect called resonance, where the frequency of the earthquake's seismic waves happened to match the natural frequency of the mid-sized buildings. Like a well-timed push on a swing set, each additional seismic wave amplified the building's vibration in its current direction, causing it to swing even further back, and so on, eventually reaching a far greater extent than the initial displacement. Today, engineers work with geologists and seismologists to predict the frequency of earthquake motions at building sites in order to prevent resonance-induced collapses, taking into account factors such as soil type and fault type, as well as data from previous quakes. Low frequencies of motion will cause more damage to taller and more flexible buildings, while high frequencies of motion pose more threat to structures that are shorter and stiffer. Engineers have also devised ways to absorb shocks and limit deformation using innovative systems. Base isolation uses flexible layers to isolate the foundation's displacement from the rest of the building, while tuned mass damper systems cancel out resonance by oscillating out of phase with the natural frequency to reduce vibrations. In the end, it's not the sturdiest buildings that will remain standing, but the smartest ones.
So that's the first video. So do you guys have already figured out the answers to the questions here?
If you only list your vacation home on Airbnb, you might attract someone looking for a quaint little studio.
The first question here is, what are the major factors of the structural vibration?
Stiffness?
And the stiffness. Any change or any natural frequency? Any different opinions here? Okay, yeah, both of you are correct. I think good job. Even as a master here. So actually, natural frequency is a function of the mass and stiffness. Right? So I would say the mass and stiffness. The most important factors determining the response of the structure under seismic vibration. Well, so how about the signal? So under earthquakes,
Middle.
all vulnerable. Low rise, middle rise, or high rise. Middle rise. Any or What's up? Any other appearance here? So any appearance from students online? And even maybe difficult for you to communicate here. You may, if you like to not hear what the parents like Nick said. Actually, we have one student that Nick said that he first initially said that meteorites are vulnerable, but he practiced his answer a few seconds later. He said that depends on the frequency.
The Mexico earthquake, it was mid-rise, but the frequency of that earthquake could be different in others, so.
Okay, okay.
The second answer.
Okay, yeah, I think very good job, Nick and Elizabeth. So it depends. It depends. Right? So it depends on the natural frequency of the building itself, as well as the frequency of the earthquake. The dinosaur, yeah. That depends. Depends. That's the depends. That's very so through this semester we will I will show you or you can derive by yourself. That's why it depends on the natural frequency and the frequency that are taking consideration. So actually through this entire semester we will talk about how to calculate the frequency of a single degree freedom system or the frequencies of a multiple degree of freedom system here, so that we can at least check the natural frequency of the building itself. And then we will do a little analysis to understand or interpret the frequency of the earthquake itself. So as you can see here, structure dynamics is the most powerful tool to better study the structure responses under earthquakes. Without the knowledge of structure dynamics, engineers cannot do good design for building on earthquakes. So if you, in the future, if you wanted to do some structure design for earthquakes, structure dynamics is a prerequisite. Okay, so that's the first video. Any questions regarding the video or comments or insights to share with all of us here? So any questions from students online?
Can you hear me? Professor, can you hear me? Can you hear me? I'm not sure if you can hear me. If you can hear me, just let me know. Professor, can you hear me?
Thank you. So when you watch the second video, please keep to this question. Only one question from the second video. What are the ways to mitigate the vibrational buildings in wind, especially for the high-rise building? So the second video will talk about the high-rise building here. And another question that I have for remote students. So how did the video playing work on your side? Did it go well?
Yeah.
Oh, thank you, Kenny. So now let me see the second video.
Oh, how we long for Old Spice.
Microban 24 protects surfaces from bacteria for 24 hours, touch after touch.
Wind is one of the most important factors that architects and engineers must consider when designing tall buildings. While skyscrapers might appear to be highly strengthened, immovable structures, all tall buildings are in fact designed with a degree of flexibility in mind. This is principally due to the impact that wind forces, known as wind loads, have on a building as it becomes taller. Whilst you might be experiencing a pleasant breeze at street level, the force of the wind generally grows much stronger the higher up you travel. While the steel and concrete used in a skyscraper's superstructure is designed to bend and flex to absorb the impact that these wind loads have, the degree to which a structure is able to move can have a significant impact on the comfort of those inside the building. When buildings first began to grow tall in the 1890s and 1900s, height limits were imposed, such as those introduced in Chicago, to prevent their masses from blocking sunlight. In New York City, ordinances were passed that allowed tall buildings to develop on the basis that they were set back after reaching a certain height. This allowed sunlight to reach street level, whilst breaking up the facade and reducing the impact that high winds had on these early towers. By the 1960s, however, larger box-like skyscrapers began to come to prevalence, bringing with them a whole host of wind load engineering challenges. The first problem that began to arise was increased wind velocity at street level. This was principally caused by the street canyon phenomenon, an effect that sees large buildings redirect wind down their facades, which effectively act like canyon walls, and funnel it along streets at much higher velocities than in low-rise suburban areas. The street canyon effect was particularly notable in Manhattan, where the heavily formalized grid structure of the city blocks offered little to break up and deflect winds once they began to blow. Additionally, as wind moved around the top of these tall structures, vortices were being created in a process known as vortex shedding. This process, much like water flowing down a stream, acts differently on obstacles depending on how streamlined they are. In the case of these buildings, their sheer block walls created a bluff obstacle that wind had to flow around. As strong winds moved around these structures, areas of low pressure emerged on the opposite side of them, creating suction forces that pulled at the buildings, causing them to sway back and forth. While any such movement may initially be minimal, high winds can create vortices that can match the frequency of the building they are moving around, causing noticeable swaying and shaking motions for those inside. This phenomenon led engineers to begin testing models of tall buildings in wind tunnels at design stage, assessing the potential impact of high winds on structures before they were constructed. By doing this, project teams were able to develop innovative approaches to managing wind loads, reducing their impact on tall buildings and enabling them to rise even higher. The first and by far simplest way to reduce the impact of high winds on a tall building is with an approach called corner softening. Corner softening sees sharp edges smoothed off of a structure to make it more aerodynamic, or small cutouts created on the edges of a structure to scramble prevailing winds and reduce the strength of the vortices they create. A prominent example is the ornamental design of Taiwan's Taipei 101, where relatively minor cutouts on the building's corners reduced movement by as much as 25%. Tapering a building as it rises also breaks up the uniformity that causes vortex shedding. Kuala Lumpur's Petronas Towers and the Shard in London both use this technique to reduce the effect that high winds have on their structures. Taking things a step further, alternating a building's profile as it rises and including setbacks can also reduce the strength of vortices as they move around buildings. Some of New York City's early skyscrapers achieved this in response to the setback ordinances of 1916. But perhaps the most notable example today is the 828-metre Burj Khalifa in the United Arab Emirates, the world's tallest building at the time of filming. This remarkable structure uses a range of techniques to tame the wind and achieve its height, including an extreme taper, multiple setbacks, and a high degree of corner softening. We've demonstrated how the Burj Khalifa's carefully crafted design manages the wind in this simulation. Developed using SimScale's software. With more than 150,000 users worldwide, SimScale is an easy-to-use, cloud-based engineering simulation platform that enables everyone to create powerful, high-fidelity simulations in a web browser. The platform can be tried for free through the community account, which gives access to thousands of public simulations to promote knowledge sharing and to crowdsource advice. Creating a twist in a building's form can also reduce the impact of vortex shedding. With every floor offset to the last, the number of bluff areas across these structures is considerably reduced, minimizing, or in some cases completely eliminating, the locations where vortices can form. Perhaps the most breathtaking example of this technique can be seen in China's megatall Shanghai Tower, which tames the wind and rises to become the world's second tallest building by elegantly twisting throughout its 632-metre height. Another way to reduce the impact of high winds on tall buildings is to increase their porosity, cutting out parts of the structure and allowing air to flow through as well as around the building mass. This technique has been used in a number of high-profile skyscrapers around the world, including Saudi Arabia's Kingdom Center and the World Finance Center in Shanghai, China. But the most impressive example can be seen in New York City's 432 Park Avenue. With an incredible width-to-height ratio of 1:15, the tower is one of the world's most slender skyscrapers and the most prominent manifestation of New York's emerging super-skinny residential tower trend to date. The 426-metre tower features double-floor cutouts at 12-storey intervals throughout its height, allowing wind to pass through as well as around its extremely thin structure. We have again demonstrated the impact of this approach in a SimScale simulation. Some buildings using this approach have tried to incorporate wind turbines into their voids in an effort to harness wind energy and convert it to electricity. Despite the obvious benefits of this, wind turbines on skyscrapers never really seem to have caught on. In addition to the techniques that tall buildings use to tame the wind, some are also fitted with dampers that counteract motion where it occurs. These incredibly heavy instruments are suspended, often on the upper levels of skyscrapers, and sway as buildings move, counteracting motion and creating a more stable environment for those inside. Several tall buildings already use these dampers, including Taipei 101 in Taiwan and the Trump World Tower, 432 Park Avenue, and 53 West 53rd Street in New York City. The advancements in wind load engineering made over the last 100 years have enabled the incredible skyscrapers we see today to become a reality. With further research underway and an incredible range of new technology innovations currently entering the construction industry, we could see tall buildings rising even higher in the years ahead. If you were blown away by this video and would like to get more from the definitive video channel for construction, subscribe to the B1M.
Article on that slim building.
Which one?
It's not, it doesn't, basically, because it sways, they didn't figure out the elevators correctly, so the elevators get stuck.
Okay.
They didn't account for the swayage.
Mm-hmm.
So like, it's super expensive to live there and you get stuck in the elevator.
Yeah, I was wondering how that would work. Like, obviously, you can't have full cutouts, right? So you have the shaft for the elevator
Mm-hmm.
and the stairs. So wouldn't that still sway? Wouldn't it
They didn't
kind of
like-
counteract the holes going through it, or no?
I know, you don't read the articles I send you.
Yeah, you send me an article. I New York Times.
I sent, it's about the Slender building, but basically there's engineering problems with it.
Yeah. J-Lo.
Yeah, I heard. Like $15 million for,
It's, you have like panoramic window views.
yeah, the whole city. It's beautiful.
Okay.
There was something else, like another problem, like something basic that,
Thank you. And I will reread that article you sent to me last
It's okay.
semester.
my feelings are, along.
Okay, Anyway, let's turn on that page. Okay. Come back to this question for that video. What are the ways to mitigate the vibration of buildings?
Softening. Well, there's softening.
Oh, yes, corner softening, like change the shape of the profile of the building. Right? Very good. So option one, we should be able to change the profile. Really? The corner softening. Okay. Okay, that's one. First. Very good. First. Any inputs from the students online? If you have different opinions, or if you would like to sum up your thoughts here, please go ahead, turn on your microphone, and I think the whole class can hear you. Right? And that's I'm not really also very quiet.
Maybe tapering the building.
Tapering.
Tapering, yeah. Yeah, the building, very good. Preparing the building. Preparing the building. The vertical direction, right? Building will have a larger footprint and a smaller footprint and higher numbers. Very good, very good. Anything else? Yes?
Setbacks and offsets.
That setbacks?
Yeah. And alternating offsets.
Alternating offset. Good. Good. So we here this video has already shown you a lot of ways to mitigate the variation of high-rise buildings winds. But which approach is associated with structural dynamics? Dampers, very good. The dampers, as you can see, the very end of the video, adding dampers can help. So when you design the dampers, we would like to know, for example, we would like to know the status of the damper, or we would like to know the mass of the damper, so that we can better design the damper. So that involves the knowledge of structural dynamics over here. And very good. And what else? Yes.
The velocity by cutting openings.
Yes, that is one way to cut okay. That facade. Yes, that helps. It does. Is that associated with the structural dynamics? Yeah. Okay. That maybe associated with the structural dynamics, but it is primarily associated with the aerodynamics, right? Because something openings will change the geometry of the building. Basically, when you do analysis, that change will change the aerodynamics of the. Yes, that's and that's a good way, but not directly associated with structural dynamics. So as you can see here, there are so many ways of here. So besides dampers, so which method is pretty associated with the structural dynamics too? So does is the tapering the building in vertical direction associated with structural dynamics? When we talk about the structural dynamics, if we say translate structural dynamics to more practical parameters such as mass and thickness. Right? So if the approaches change the mass or the thickness of the building, that means that is associated with the structural dynamics over here. Right? So is tapering the building in vertical direction, changing the thickness of the building or the mass distribution of the building too? So yeah, tapering the building in vertical direction changes the mass distribution, because you will have more mass upper level, pure, lower mass on upper level, and then you also change the stiffness later. And that is also associated with aerodynamics. So it's a combined structural dynamics and aerodynamics. So that's the question about the second video. As you can see here, designing high-rise buildings is not easy. That's your interest.
What I want to do.
Yeah, so probably you have also to take aerodynamics from mechanical engineering. Just kidding. So, yeah. So, there is a wind tunnel run by the mechanical engineering department. Yeah. I think you.
Friends with the mechanics?
Yeah, among my friends, but you have to figure out a reason to do their content part. I think all the equipment run by SETA can be used by students. All equipment and machines shared college. But there are some people managing those. Talk to them to give them a reason. And the wind tunnel is I think it's a good resource if you are interested in doing any research, for example, undergraduate or graduate research. I think you should be able to. So that's the second video. That's the second video. So any questions from students online? Do you guys need add any here? Okay, so if you know any questions here, I'm just gonna play the third video. Or in the millennium. I have already prepared this question on one note about that something wrong with my time, but then it's the big fix. Okay. So how did the engineers fix the undeniable vibration of the London Millennium Bridge? That's the question for the third video. So everybody ready for the third video? Okay.
Take a trip beyond your backyard. Compare your way there. Find the smartest credit cards for you on NerdWallet.
Chocolate, peanut butter, and oh dang, nougat's here? Now it's a party.
When buildings go bad, not all engineers have the luxury of fixing them on the quiet. Some fails you just can't keep under wraps. Force isn't a conscious choice, but how we've evolved to stay upright, as civil engineer John McDonald demonstrates.
So what we have here is a very simple representation of the human body. We've got the centre of mass or centre of gravity, which is roughly sort of tummy height, and then we're standing on our feet down at the ground, which is below that. So we're essentially unstable because we've got the mass up here, but the support down here. And so if we don't do anything, then we'll fall over. But what happens is, rather than falling over, we adjust the position of our centre of pressure under our feet. So rather than falling over, we move around in the same way as we move the centre of pressure under our feet to keep balance.
The crowds walking in time, side to side.
Imagine if manufacturing automation was simple. Introducing Vention. One platform.
The important thing is that they put their minds together and came up with a really simple solution that didn't impact the striking design.
Very good video. Okay, so now let's go back to the question here. How did the engineers fix the aero vibration of them in the new bridge? Yes, morning.
They put dampers on
Yeah,
it.
dampers. Very easy fix. But how long did it take for the engineers to year and a half? Just adding those small dampers there. Why it took a year and a half?
Animal.
Yes, yeah, it takes time to do the testing, right? Secondly, for you is if you know adding dampers will fix that problem here. How many dampers would you like to use? Where to put the dampers?
The design of the bridge intact.
Right. And what type of damper would you like to use? What properties would you like to expect from the dampers? Which manufacturer would you like to talk about the dampers? So before you finalize the design to fix that problem, all you have to get the answers to for all those questions. So that takes time. We have to do run analysis, a lot of calculation, and testing is one of the most important steps. And so after you finalize the design and the repair or of the retrofit of the bridge, you have to test to make sure it works that you have already banked it or designed over there. So all of them takes time. So and all of the tasks here are related to structure dynamics. And here, so that's 3 videos for tonight's class. As you can see here, whether you design low-res building, mid-res building, or high-res buildings, you have to deal with the frequencies of the building and to be able to calculate the natural frequencies of the building so that you have some background in structural dynamics here. So that's why this semester, most of the engineering schools, they offer structural dynamics in civil engineering program. And so that's why we decided to offer this course this spring, and hopefully we will offer this course and it's a more frequent, the higher frequency, I would say, over here. So that's the some background about the core application of structural dynamics in both building and bridge industry over here. So today I'm just going to give you more scope about this course. So to on the sharing, so I'm gonna share my surface here. I'm just gonna is the first thing for tonight's class, besides some introduction videos, I like to so also have some objectives for tonight. The first objective here is to interpret the process of different interpret the sources of different dynamics. The reason why we need learn structural dynamics is because a lot of structural loadings themselves are dynamic loading rather than static loading. I would say in the real world, all the loadings are dynamic loading. So this is the first. Second one is to structural models. The first step for structural dynamics is to be able to simplify the real-world problem to a structural problem. So, formulate. As long as we have the structural model, what you formulate the equations. So the start of structural dynamics. Formulation of equations of motion. The font size readable for you guys, or do I need to read in our? You okay? Please let me know if the font size is too small for you. In our yeah.
Programming. Well, are you using your personal laptop?
Yeah, I'm using my personal. computer thinking in every class.
IT should hire me.
It'd be better than they got now.
So now let's talk about the overall overview of structured dynamics. Overview. Structural. I think this is the first class that you will deal with the structures under dynamic loading. So previously, due to structural analysis, all the loads are supposed to be static, and all the analysis methods based on the table diagram and the ratio of equilibriums, as well as the load force and displacement relationships. So all of them are based on the static approach. But starting from today, we will talk about the analysis dynamic form. So the load itself is dynamic. So that means that the magnitude of the force varies. So now let's talk about it. Since it is structural dynamics, we will talk about structures. In some schools, they also offer a soil dynamics, different course. And in mechanical engineering department, they offer a course called vibration. Actually, that's the dynamics of machines, like the dynamics of cars, aircrafts, ships. So that's the work of mechanical engineer. For civil engineers, the work of us, we will focus on the structures. Structures. For the object, and that we will focus on here for this course, mainly structures. Sometimes we will talk a little bit about the vibration of vehicles, types of not civil engineering factors, but just to show you that the approaches that we need here should be applicable to other cases. For the future, if some of you like to be a mechanical engineer or design aircraft, the theory as well as the approaches you learn from this course should be applicable to the other cases. The only difference is when we have a different structure other than the civil engineering structure. But here, our main focus here for this course will be sometimes for pipeline. Pipeline, we have vibration issues. Focus. So focus of so different from the static analysis, we will talk about the dynamic analysis. That means the forces are dynamic. Dynamic excitation. Can you name any dynamic load over here for structures?
Oh,
A weak on the bridge, very good. So weak load. Good, very good. Okay. Blast. Okay. Blast loading.
Then your bridges are blast proof.
So any inputs from students online? Please do not be shy. And then also expect some participation from you guys online. Seismic activity? Okay. Yeah, seismic. Okay, very good. Thank you. Seismic. You know, so the expectation maybe on the bridges or buildings, or any civil engineering structure here. Wind. So anything else?
People.
Oh, yes, live load from them and then.
Jobs, right?
Very good point. Good point. And very similar to the wind load. So the wind load that itself is a dynamic. Good point. Yeah.
Thermal expansion and all.
Expansion. Sometimes, but most cases the very good the duration of the thermal expansion is and be regarded as at least a quasi-static. Anything else?
How about earth pressure?
Could you please, Keshav, could you please say it again?
I was saying earth pressure.
Earth pressure?
Barometric
The earth pressure, typically, if the duration of the effect is very long, so in reality, most of the load are dynamic, but we should be able to take the earth pressure as a static load because the duration takes much longer than the other load. A very, very good point. Very good point. So typically when we talk about structure, like how about the impact here? Impact loading. So do you have a car hit the column of the one building or the tier of a bridge? Right. Yeah. So that's the impact. So all of these are dynamic. So those are dynamic. So when we do the structural analysis, we usually have those nodes as input. So those expectations will be applied to the structures. So we will have the response. And we have the response of the structure. And so there are two types of response. So the first type is called rigid body. Body response. For example, we have a two-story building. And under earthquakes, the ground moves. The ground moves. So the rigid building moves with the rigid body as a rigid. This is the first type of response. So the second type of response is deformable. Under earthquakes. There are some deformation in the columns of the building, the beams of the building. I would say that deformable response is more in the real world. So that's so basically the process of structural dynamics analysis is to have the input of different types of dynamic loads to the structure, and we need to figure out what is the response of the structure. Rigid body or deformable. So that's the typical procedure of structural dynamics analysis. Dynamic analysis. So, so that's what we will do through this entire semester. Consider different types of load and we have different types of structure. And we apply the dynamic load to see what will happen to the structure. To know the maximum displacement of each floor of the building. Like we know what is the bending moment, the shear force, or the axial loading each member of the building, so that we can do design based on the dynamic analysis. So that's so different from the static analysis here. So any questions regarding the overall scope of structural dynamics here? Overall scope of the dynamic analysis here. Okay, so if you know any questions here, let's talk about wind load. Let's see what is the case. So, take as a power of a a suspension bridge here. For example, we have a suspension bridge. So this is the power of the suspension bridge. So we know that there will be cables coming particular to the cable to the power, and we have some cables in the deck. So the suspension cable and this one to the main cable. Is the animation view from one end of the bridge to the other end. And then this section view makes sense. So this is George Washington Bridge or Golden Gate Bridge. You stand on the side of New York City to see the bridge. From the New York side to the New Jersey side. See it. And if there is a weight, so when we do design, typically we would like to consider the self weight of and the gravity of the deck. Gravity of the deck. If there is a wind, there should be some forces acting on the deck induced by the wind. Drag force, DT. Lifting force. There is wind blowing from the left side. Basically, the deck of the suspension bridge will be subject to a drag force in the horizontal direction and the lift force in the vertical direction. And different from the static analysis, here we need to fit both forces, the drag and the lift forces, as the variant to the time, as a variant to the time. Two forces here. Both forces are variant. This case, and then this is much closer than a classical analysis to the real. So any questions here? And typically these two forces can be measured in the field. For example, we can install a lot of pressure sensors so that we can measure the pressure acting on the surface of the tank that we can form the time varying of these two forces. So any questions from students online? Okay, so if you know any questions, and in this case, these two forces are also depend on wind velocity. The E equal to F B ALT equal to E. So that we should be able to kind of design node, right? Design codes. So the design codes, so that since these two forces are functions of the window velocity, so the design codes can give us equivalent static load based on the velocity of the velocities of the wind. How many of you have already used the ASC7 to calculate wind load? So how did you do that?
Well, you go into, I mean, there's different chapters in it, but you go and you find your state, and then you find like exact location, and it pretty much gives it to you based on certain areas of location.
Mm-hmm.
For wind at least, but for other loads, it's kind of tricky.
Yeah,
there's a bunch of options for like different roof material loads and different dead loads and live loads that you could put in there.
Yeah. So so ASC7 provides a chapter for wind load, and firstly you need to figure out the design wind speed for the location where the building or the bridge is located, so that you can calculate the equivalent static load, the function of the wind speed over here. So that's so basically that means ASC7 has already done the dynamic analysis for engineers, so that they just gave the equivalent static load for you to do design. But actually, the way to use a dynamic load, and the ASC7 not suited for some cases. If you take look into the details of SC7, SC7 is limited to some standardized or specific structure types. So SC7 is not suited for So in some cases, you may not be able to use the design code to extend the window, especially if you have very long slender structure. So in this case, you have to use the wind color. Yeah, you have to use the wind color to do some testing and measurement to figure out the actual wind load that you apply, because the load itself is also a function of the frequency of the building. So that's the one case where we need to use structural analysis based on the dynamic theory, on the static theory. And the next time we will also talk about the cases where we have blast loading, seismic loading, and line loading. So that's the topics we will also go over about the scopes view of the dynamic loading in different cases here. So I think we do not have time to finish the blast and pack loading tonight, but next time. This week we did not have any homework. Typically, first week it's a party week. But starting from next week, I will give you homework for each week. So each week you will have to do refresh on one task. Figure out which and learn the new stuff. I think that's all for tonight, and good to see you again on campus, and good to hear some of you for a while. And that's all for tonight. And all the notes will be uploaded to the Blackboard. And the lectures is being recorded. So I think don't worry if you miss something here.